I'm going to talk about section 2.2 today, basic differentiation rules and rates of change. So the whole point of today is finding sort of tricks to do these derivatives much quicker than we did in 2.1. So 2.1, using that long drawn out definition of derivative process, will be taking place using these different rules, which will make our life a lot easier. So from here on out, if you're asked to find a derivative, you're going to do the easy way unless it specifically says use the definition of derivative. Okay, so you definitely don't want to make the mistake of using definition of derivative when you have access to these. So now, from only when we're specifically asked to use definition of derivative are we going to do that. Okay, so these rules you want to get down in your notes. I'm going to talk a little bit about these, but for the most part, get these down in your notes. They're basic formulas, and then we're going to end up doing a bunch of examples with these. And you're going to find that this makes things go really quickly. Okay, so this first one, by the way, this d over dx notation means take the derivative of this thing in terms of x. I'm going to talk more about these notations at some point, but right now I think it's fine if we just leave it. So d over dx of c, c being any constant at all, if we take the derivative of any constant on its own, we get 0. And if you think about a constant function as just a horizontal line, the derivative of that is going to be 0. It makes sense. Okay, this next one, we take the derivative of x to any n. N can be any rational number, so we can use this one to deal with like fractions, like if x is in the denominator, we can make n negative. We can also use it to deal with roots, like the square root, we would use n equals 1/2. But what ends up happening is the n comes down and then that drops a degree, okay? This is called the constant multiple rule here. By the way, the names of these are in the book. I'm not all that interested in them as long as you know the idea. So if we take the derivative of any constant in front of f of x, so a constant multiplied by f of x, it's important that we're just talking about a constant. Because down the line, and I'll talk about this in a moment. So if we have a constant in front of f of x, it's going to be constant times whatever the derivative of that thing is. Okay, this is a sum difference rule. Basically, it's kind of intuitive. If I take the derivative of sum and difference, I can take the derivative of the parts and then add or subtract them. The thing that's important is you'll notice that we're not doing a multiplication or division rule. So the derivative of f of x over g of x is not just f prime over g prime. It is not. Same is true if we do a product. If we take the derivative of f of x times g of x, it is not f prime of x times g prime of x. So if you remember, I talked about how limits always play nice. With limits, you can do those types of things. With derivatives, we can't. The only time we can sort of split it up how we would intuitively think is with when we're adding or subtracting them. Okay. So let me erase this because you cannot do that. Down the line, we're going to learn how did they take the derivatives of products and quotients using product or quotient rule. Okay. Derivative of sine x is cosine x. The derivative of cosine x is negative sine x. And at some point we'll talk about how these things work graphically. And then the final derivative is the derivative of e to the x is e to the x. That is actually the only function that it's its own derivative. Okay? So the derivative of e to the x is e to the x. So those are your basic differentiation rules. Please get those down in your notes. And now we'll do some examples with these. Okay, so we're going to do some examples here. Actually, I'm going to do more in this. You'll see when you look at your textbook, I did assign a lot of problems because it does take practice, but I will show you can get through these pretty quickly. If we were to do all these using definition of derivative, it would take us so much time, and some of these would even be unreasonable to do. So let's go ahead and go through these quickly using the properties I showed you before. So the derivative of 3/7, well, that is a constant. The derivative of any constant is just simply 0. Okay, so this one we're going to use, this is simple power rule. So anytime we have x to some number, we bring down that number, and that drops a degree. Now, if we have something like this, we have to write it so it's in that form of x to the nth. So this one, of course, will use a fractional exponent. So this we'll call x to the 3/4. And what you're going to see with a lot of these, we're going to want to rewrite it in a form that we can use one of these rules quickly. So g prime of x is equal to 3/4 x to the negative 1/4. Okay. By the way, when we're just turning out derivatives like this, I have no problem with you leaving the negative exponents in it. In this class, which is unlike previous classes, typically, unless you're specifically asked to simplify an algebraic thing, you don't have to. So this is perfectly fine. If you look in our textbook will always simplify those, but honestly, this is not an interest of mine, especially when we're sort of practicing a bunch of these. I'd rather you go on to the next problem and do it. Okay, so this one we're going to rewrite as x to the negative third using a negative exponent. We always want things in that form of x to the nth. So now we have f prime of x equals negative 3, x to the negative 4th. Okay, this is one we want to be careful with. Notice we're taking 7x, the whole quantity squared. That means 7 is being squared and the x is being squared. So that's going to be 9 over 49 x squared. And then I rewrite that thing. Let me rewrite it here. Y is equal to 9/49, right? So just that fraction in front. And then this is going to be x to the negative 2nd. Now, what ends up happening with our constants is this. Constants in front, we just are going to take this thing, the derivative on its own. So the derivative of this is going to end up being negative 2, x to the negative 1st. And then we have the 9 over 49. Okay? So the one thing that ends up happening here, and I did this in 2 steps, down the line, that's going to be a bit overkill. But what ends up happening is when we have a constant in front in this case is that negative 2 will come down and I'm going to multiply that. So instead of just leaving it like this, I'm going to go ahead and multiply this. Now one thing I want to say is I know right now, I'm letting you use your calculator for a lot of things I wouldn't normally let you use your calculator for. These are all closed calculator. You should not be giving me decimals. If you give me decimals in this context, that's a problem. These should be fractions here. So that negative comes down. I end up having y prime is equal to negative 18 over 49 x to the negative 3rd. Okay? So that is that derivative. So the negative comes down, multiplies, and that drops a degree. Now this is a combination of them. This is really easy. Polynomials are really easy because we're adding and subtracting. We can just do this as 3 separate derivatives. So we just sort of do this intuitively. So adding and subtracting sort of works intuitively. So the 4 comes down, that's negative 4, x to the 3rd, plus the derivative of 3x. Realize that this is a 1. The 1 comes down, that's 3, okay? And then we get x to the 0. Well, x to the 0 power, anything to the 0 power other than 0 is 1. So that just is 3. The derivative of 9 is 0, so that is my derivative. Okay? So let's rewrite this one here. So g is equal to x to the 1/2 plus 3x squared. So our derivative is g prime of x is equal to 1/2 x to the negative 1/2 plus 2 times 3 is 6, x to the 1st or just x. Okay? Notice we're doing these pretty quickly. Once you get the hang of this, you're going to find that this is pretty easy. Okay, now I cannot take the derivative of the top and put that over the derivative of the bottom like I can with adding and subtracting. Anytime we have a product of different variable terms or a quotient of different variable terms, like we saw with these, you have to rewrite them so it's not in that form. So one thing that we're going to use a lot of in this class is we're going to use this idea that if I have something like a plus or minus b over c, I can split that up as a over c plus or minus b over c. Okay? So what I mean by that is I can actually rewrite this thing as y equals x to the 3rd over x squared minus 3x squared over x squared minus 5 over x squared. So each one of those gets divided by x squared. If you want to think about it this way, it's kind of like distributing division, right? And if you think about it, that makes sense because division and multiplication is the same. So we would have no problem if the x squared was being multiplied, we would distribute it. Well, the same thing basically happens with division. So I'm distributing the dividing by x squared. Let me go ahead and erase this because I'm running out of room here. So after we simplify this, we're going to get x. So x to the third divided by x squared is x minus 3. X squared divided by x squared, that is just 1, minus, and that'll be 5x to the negative second. Now it's in a form that I can take the derivative. Y prime, the derivative of just x, the 1 comes down, gets multiplied, and then that drops to 0. So that's actually 1. Another way to think of this is x is just a linear function with a constant slope of 1, so the derivative is just 1. This goes to 0, constant, I'm taking the derivative of constant. This one, negative 2 comes down, that gives us plus 10x to the negative third. Okay. Cosine. Cosine is just a matter of memorizing. This is a constant multiple rule thing. So anytime we have a constant multiplied out front, we'll just leave it there. The derivative of that will be 3, and then cosine is negative sine x. Okay, and then, generally the way we're going to write this is negative 3 sine x. But once again, if you left it like that, I would give you credit. Okay, this last one, once again, we've got to write this thing so it's not a fraction, which is pretty easy. I'm just going to write it as a fraction in front. So this will be g of x is equal to 2/3 sine x. Now we have the constant out front. Use that constant multiple rule. So this will be 2/3 cosine x. So I didn't time myself, but that didn't take very long. The hardest part about these is probably just rewriting them. So that is 10 examples. I actually am going to do a few more here. Okay, so let's continue on with example 1, a few more of these. So once again, as soon as I see this fraction, this quotient, I know I've got to rewrite this so it's in a form that we recognize from our rules. So this we'll call 1/2 cosine x, and then plus. Now let me point out to you, I basically know I don't have to deal with this because, we know cosine of pi over 2 is 0. But the derivative of any constant, and I know this is going to be a constant. All right, so this is just some constant here. I don't even care what it is. So now when I take the derivative of this thing, the derivative of cosine is negative sine, so I'll call this negative 1/2 sine x. The derivative of c is going to be 0 of our constant. Okay. Okay. 12. Take the derivative of this. Constant multiple rule. The derivative of e to the x is e to the x. You have the 5 in front, so it is its own derivative. Over here, split it up. F prime of x. Derivative of e to the x is e to the x, minus the derivative of 4x is 4. And last one, y prime is equal to the derivative of 7 e to the x is 7 e to the x. The derivative of cosine is negative sine, negative and a negative, that'll give us a positive sine x. And there I did 14 derivatives relatively quickly. We're not using definition of derivative unless we're specifically asked to. Okay, let's do some other examples here using derivatives. Okay, our next example, one of the things you're going to do a lot of in the next couple weeks is writing equations of tangent lines. That's the whole point of derivatives. They give us the slope of tangent lines. So we want to find the equation of line tangent to f of x equals the cube root of x at x equals 1. And another thing I'm going to do, in some of these they do ask you to sketch graphs and sort of show those things, so we'll go ahead and do that as well. So first of all, basically when we do these things, we're going to need 3 basic ingredients. We need an x, we've got that. We're going to need a y, and then we're going to need a slope. And the form that so we have the x, we need the y and m. So this is pretty typical. And the form we typically go with, and once again, we really don't care to have the most simplified form. So in the past, when we've written equations of lines in past classes, you were probably sort of pushed always to use the y equals mx plus b form. Totally not necessary here. In fact, a lot of times we prefer the point slope form. So the point slope form, all we need is a point and a slope, and that's typically what we have, okay? I typically write things in this form. You're also welcome to write them in this form. I think this is the sort of CPM approach. So I know a lot of students do use this form. It really doesn't matter to me, but I would choose one of those. The thing about doing slope-intercept is it's going to take you more time, right? And time is a factor, especially if we're testing. And you could take more time and then end up getting something wrong because you do a little arithmetic error, nothing conceptual. So we don't want to lose points that way. All right, so let's get the y first. So the y, of course, we're just going to plug 1 into this. Now this is a no-brainer. The cube root of 1 is 1. So now I have the y. Okay, now to get the slope, right, we need to take the derivative. Before I can take the derivative of this, I need to write this in one of that form like x to the nth. So we'll call this x to the 1/3. Now when I take the derivative, I get 1/3 x to the negative 2/3. Now, before we were just turning out derivatives, I would say just leave it like that. However, we have to sort of understand what this means. So I'm going to simplify it here just because I have to work with it. So anytime you have to work with a derivative, I would suggest simplifying it. So this is going to be the 3 in the denominator, and this will be x squared and then the cube root of that, right? So now, if I do f prime of 1, I'm going to get 1 over 3, the cube root of 1 squared. Now, of course, the cube root of 1 squared is 1. So we're just going to be left with a slope of 1/3. Okay? So now my equation, y equals 1/3. Oh, sorry. Like I said, I don't care what form you use. Y minus 1 equals 1/3 x minus 1. And that's our equation of our tangent line. Okay. Now, let's go ahead and give that a sketch. This function, y equals a cube root of x, comes up quite a lot. At some point, you might even really memorize it. But you're welcome to use your graphing calculator. And I would suggest taking a look at these. There's some exercises in the book where they have you graph both. I think those are good exercises. It kind of hammers home this idea of when we're finding the derivative, we're getting the slope of the tangent. So anyways, y equals cube root of x. Looks something like this, okay? It actually goes vertical there. I talked about it when we talked about differentiability. It's not actually differentiable at x equals 0. The tangent line at x equals 0 is completely vertical, x equals 0. In this case, we're not doing x equals 0, so we don't have to worry about that. We're doing x equals 1. So then our tangent line is y minus 1 equals 1/3 x minus 1, okay? So in this particular case, you can see that the slope of that is about 1/3. Okay, so that is an equation of a tangent line. I got one more example, and then we will be done with the video for 2.2. Okay, example 3. This is the setup for the problem. I want you to get this down in your notes. This is getting to a type of problem called vertical motion problems, which is something we're going to be seeing in different contexts as we move throughout this chapter. So a water balloon is thrown upward from the top of an 80-foot building with an initial velocity of 64 feet per second. The height s in feet of the balloon can be modeled by the position function s of t equals negative 16t squared plus 64t plus 80, where t is time in seconds since it was thrown. Okay. Vertical motion is something that you also do in physics if you've had that course. If you're looking at this and going, wait a second, that's not the correct formula. I want to remind you in physics, you pretty much exclusively work with the metric system. So this would be not feet, but meters. We do both in here. And we'll be talking more about where this comes from and why we always get these formulas. But please get this down, this problem situation. I'm going to have to erase here so I can actually do some problems. Okay, so get this problem situation down. Okay, So we're using up a lot of room here. So once again, here's our position function. Keep in mind, S is measured in feet, T is measured in seconds. We're going to do part A, B, and then when we've done these, I'm going to do a part C. Okay, so part A, find the average velocity on these intervals. So average velocity, I want to remind you, so let's look at our graph here. So our graph is going to look something like this, okay? Average velocity, and I don't know exactly what this looks like, average velocity is the slope of secant lines, okay? So when I'm asked for average velocity, I'm doing the slope of the secant line. So if you remember from CPM, they talk about AROC and IROC. AROC is the slope of the secant line, 2 points, okay? So pretty basic here, don't need any calculus for this. So I'm doing S of 3. So I'm taking 3, I'm plugging in there, minus S of 0.5. And then that's over 3 minus 0.5. Okay. Now, there's really nothing to do other than plug that in our calculator. May I make a suggestion and plug this in as y sub 1, and that way you can just quickly, get this on your calculator. So I just went ahead and plugged this into my calculator already, and I get 8 feet per second. Don't forget our units here. Okay, 1 to 4, so that'll be S of 4 minus S of 1 over 4 minus 1, and that is giving me negative 16 feet per second. Now remember, when it comes to velocity we can have negatives. Speed we don't. When we talk about speed, it's always a positive. So my average velocity from 1 to 4 is negative 16 feet per second. In this particular case, a positive velocity means I'm going up. A negative velocity means I'm going down. So the fact that I have negative 16 from this interval means maybe for a period of time I was going up, but the whole net gain has been down. I went down more than I went up over that time interval. Okay, so let's do these velocities. Now, the velocities we're talking about IROC. So for instance, if I'm doing the velocity at 1, I'm talking slope of a tangent line. And at t equals 4, I'm doing slope of a tangent line as well. Well, in order to do the tangent line, we need the derivative. So we're going to take the derivative of this thing. So the derivative of our position function gives us our instantaneous velocity. Okay, so this is actually quite easy. Bring down that 2, that's negative 32t plus 64. Now it's just a matter of plugging these things in. So S prime of 1, or V prime of 1, however you want to label it, is negative 32 plus 64. I don't know why I'm writing it out like this. So this is equal to 32 feet per second. So the fact that's positive means at t equals 1, we are going up. The balloon is still going up. At t equals 4, so V of 4, or S prime of 4, is equal to negative 96 feet per second. So like I said, we have the negative, it is going down. Okay, we have one last part to do, part C. Okay, actually we're going to do 2 more parts, C and D. These are actually related. So part C, how long is the balloon in the air? So if we think about this, S of t is its height. So how long it's in the air, we want to know when S of t, or excuse me, when the balloon hits the ground, which means the height of the balloon is going to be 0. So I'm going to set S of t, which is equal to this function, equals 0. Now, when it comes to solving quadratics like this, typically they're either going to factor, especially if it's a closed calculator setting. If it doesn't factor, you can use a quadratic formula. If you have use of your graphing calculator, you could always just graph it and find your 0 there. Any one of those methods will work depending on whether it's closed or open calculator. Okay, so I'm going to factor out a negative 16 here. I'm going to factor this, which is going to leave me positive t squared minus 4t, and then that's going to be minus, and then 5 is equal to 0. So this is going to factor. So I'm going to get negative 16 t plus minus, so this is going to be 5 5, and 1. So we actually get two possibilities, t equals -1 and t equals 5. So t equals -1, realize that this does not make sense in this situation because a t equals 0 is when the situation begins. So I'm only looking at the t equals 5. So the balloon will hit the ground after 5 seconds. So it's in the air for 5 seconds. Now that brings us to part B. What was the balloon's velocity the moment it hits the ground? So once again, that's an instantaneous velocity. Exactly the moment that t equals 5, what's our velocity? So once again, our velocity function, v of t is equal to s prime of t, which is equal to -32 t plus 64. And oh, I did the wrong thing. I have to make it okay. So anyways, v of 5 is equal to, just plug 5 in, that's -96 feet per second. You guys probably already caught this. So this is the velocity that the balloon is at when it hits the ground. So I got to make a fix. In the part before this, I said the velocity at 4 was this. My mistake. V of 4 from part, what was that, part B? V of 4 was not -96 feet per second. It was -64 feet per second. So please make that change if you haven't already. All right, so that is section 2.2 done. Now from here on out, we can use all these tricks to take derivatives.